In the last lecture, we looked at data that is not complex, in particular because it is linearly separable. Big data, on the other hand, is complex, and so we're going to introduce big data by taking a first look at what it means for data to be complex. We're going to look in particular at complexity via dimensionality. And to get started, let's just say we look at the simplest case of logic spaces. So a logic space is where you have variables x and y representing the truth or falseness of statements or propositions. So the AND logic space says that if I have two statements that are both false, then false and false is false. We're going to assign 0 to false and 1 to true. So this row means if x is false and y is false, then the two together, x and y, are false. Likewise, if I've got a proposition, for instance, let's suppose that I've got a proposition corresponding to x of a dog has 4 legs, and a proposition corresponding to y of there are 8 days in a week. Then x is true and y is false, and so if I have the compounded sentence with and, a dog has 4 legs and there are 8 days in a week, that is a false statement. So likewise, true and false is false, false and true is false, but true and true is true. The OR data set is similar. False or false is false, but now if I say a dog has 4 legs or there are 8 days in a week, that statement is true because one of them was true. And so there we get the OR data set. Now the XOR data set is like the OR, except that we're going to exclude the possibility of both being true by saying that that is also false. So this is the XOR class. Now let's take a look at these geometrically. So I can plot these as points in the plane. Here I have, for the AND data set, I have 0, 0, 0 corresponding to these points, these first 3 points, and because they're all class 0, the locations corresponding to these points I label with 0. This last one, however, you'll notice is 1, 1. That's this position in space, and because it's in class 1, I put a 1 here. Now most importantly for us, we notice that's linearly separable. Now we look at the OR data. So notice it's the same points, however, the OR data labels the classes differently. And so we have the 3 classes, or the 3 points, 1, 1, 1, that are in class 1 in the OR data, and we have the single false, which is at the origin. And once again, those are linearly separable. But what about the XOR? Notice that when we change this last row from class 1 to class 0, representing the exclusive OR, now we can no longer separate these with a straight line. A straight line here would leave a 0 on this side, a straight line here would leave this 0 on that side, a straight line here would leave a 1 on this side, so on and so forth. However, we can introduce a new variable. This new variable z is going to be the absolute value of x minus y. Notice that I'm going to use false, true, true, false, so you can see that representation better geometrically. So let's go ahead and look at what happens when we add the z. Now we take the absolute value of x minus y is 0. 1 minus 0 is 1, absolute value 1. 0 minus 1 is negative 1, but an absolute value of 1. 1 minus 1 is 0, absolute value of 0. If we take this system and rotate so we can also see the z-coordinate, then what we notice is that very clearly we can separate the trues from the falses. In particular, we can separate them using a plane. In this case, the plane is z equals 1/2. So there we have it. This problem is, in its original statement, is not linearly separable. But we see that we can define more variables and separate the problem. In particular, we can embed a data set with m features into a data set with n more than m features. We could do this explicitly by simply defining new variables, absolute values and things like that. Or we can do it implicitly by defining a transformation, typically not a linear transformation, that maps from the lower dimensional vector space into the higher dimensional vector. This gives us the ability to make a working definition of big data. In particular, a big data classifier data set is linearly separable only after embedding into an extremely large dimensional space. So that is, we're taking a data set that has original dimension m and using some kind of a transformation to embed this into a space with dimension n, where n is much, much larger. Now the key here is that using the data set itself, the m given features, we can't linearly separate. We also can't define one or two or a handful of new variables and accomplish that linear separation. In particular, we get such linear separation only after the embedding. And this n must be much larger. In fact, in most of our examples, n is so astronomically large we can't work in the space anyway. We only pretend to work with the embedding. So here's an example. So genetic activity is collected from 7 subjects during an experiment. This experiment activates some of the genes, but not all of the genes. And so we want to know which genes are activated or expressed because of the experiment that took place and which are not. So that's our class 1 is those activated, class 0 those not. This is a big data set. It's large. It has 22,645 rows, and it's complex. Here's what it looks like just using subject 1 versus subject 2. And pretty much any way we try to group the subjects, we get these kinds of images. There is no way to separate the ones and put them on one side of a line, or a generalized line, which is a hyperplane, a plane in 3 dimensions, hyperplane in 4 or more dimensions. And there's no way to end up with ones on one side and zeros on the other side. The data is just too complex. Now here's another viewpoint that's somewhat equivalent and is also very helpful in us understanding what's going on. Let's look at systems or networks, or what the mathematicians would say are graphs. These are collections of nodes joined by edges. Now I've drawn 3 of these graphs, and we would say all of these are very simple, and one of the reasons they're simple is because we can draw these in 2 dimensions without any of the edges crossing each other. And you can see that, in fact, these 3 have that property. However, these networks, these graphs, cannot be drawn in 2 dimensions on a flat plane without having edges that cross. However, if we can consider a surface in 3 dimensions, the surface of a sphere, the surface of a polyhedron, something like that, then we can find surfaces in 3 dimensions in which we can draw these graphs without having any of the edges cross each other. So I'll give you the answer to the first 2 and a hint for the second one. The second one you can think of as a Möbius strip. That's a strip of paper with one edge twisted, a half twist. The first one, you can see the polyhedral structure that this graph can be drawn on without having any of the edges cross on that polyhedron. But now here are 2 graphs, 2 networks, both real-world networks, that are clearly not the type of things that you could draw on low-dimensional surfaces. In other words, if I wanted to draw these graphs on a surface being like a sphere or a plane, only drawing such things in high-dimensional context, then the surface that we use would have to be so complex that in order to embed that surface into a high-dimensional vector space, the dimension would have to be extremely high. So, big data means that there's some underlying structure that is only accessible in a very high-dimensional context. This is only a working definition. In reality, we'll probably never be able to say with complete certainty what big data really means. But all the big data things that we've looked at so far, and the things that you see out there now that are being called big data, they all seem to share this characteristic. And we can use this idea to provide some valuable insights into what it means to work with big data. In particular, there's a thing called the curse of big data. Now, big data is both large and complex. Complexity refers to an underlying structure which is high dimensional, and working with such data requires methods that are simple only in high dimensional settings, such as linear separation or drawing without having any edges cross. Here's the curse. There are huge varieties of patterns in any big data set, but only a few are meaningful. So in other words, when you have an extremely high dimensional surface, or you're working in an extremely high dimensional space, there are lots of low dimensional predictions that can be made that really are false predictions. So what this means is that the curse of big data, in layman's terms, says that you can find pretty much anything in a big data set. Sort of analogous to this idea that you can find any number in the digits of pi. So the idea is that big data, the curse of big data, is that you can find anything. However, the things that are valid predictions are few and they're not easy to find. So, in summary, big data is large and complex. Complex roughly means high dimensional. High dimensional tends to mean linearly separable only in spaces with large orders of magnitude dimensionality. So you can think of dimensions like 10 to the 54th, or one dimension for every grain of sand on a seashore, something like that. Now, it could be that we might think, well, do we ever run into such data sets? And the answer is yes. In fact, large complex data sets are the norm. And even using just a simple cell phone, you can very rapidly collect very meaningful but very large and complex data sets. Social networks, biological systems, smartphones, email networks. We're going to have to create large complex data algorithms. In other words, algorithms that work in high dimensions rather than looking at only parts of the data and producing false predictions in low dimensional settings. So this is what big data is all about. It's all about data sets that we are getting pretty much as the norm with this high dimensionality that you must address